So this is one of the very interesting problems which uses recursion, right? It's a very standard problem. There is even Wikipedia article on this problem. It's a very interesting problem, but now let's see how to tackle this problem step by step, right? So this problem is called as the largest, sometimes also called as the maximum sum subarray problem. Here I have added this word contiguous here to insist the fact that what we want are subarrays, not subsequences. So typically whenever you hear this word subarray, it typically implies that what you want is a contiguous part of an array. Whenever you hear this word subsequence, it means non-contiguous. Typically, again, sometimes you could also ask for clarification, right? So subarrays basically means contiguous in general in data structures and algorithms. Subsequences basically means non-contiguous. For example, when we learned dynamic programming, we learned about longest common subsequence, right? In the case of longest common subsequences, we were not looking at contiguous arrays. We were looking at non-contiguous arrays, just to give you a context. Again, you can go back to our dynamic programming algorithms and check out the LCS video if you have forgotten what LCS problem is. Again, back to this topic. This problem says, given an array like this, okay, so let's assume this is n, so this is 0. In this instance, we'll assume that all of our arrays start with 0 indexing and n is the number of elements. In this case, n is equal to 8. Okay, now comes the interesting problem. What is the largest sum subarray basically means? It means I want a contiguous subarray. For example, if I take this subarray, imagine if I take this subarray, this is contiguous. What is the sum of all the elements here? -2, -3, -5, +4. The sum is -1. So if I take this contiguous subarray, let's say if I take this contiguous subarray, okay, what is the sum here? -3 plus 4, which is 1. 1 plus 1 is 2. 2 minus 2 is 0. Similarly, if I take this contiguous array, okay, -2 plus 1 is -1 plus 5 is 7. Sorry, -1 plus 5 is 4, sorry. Right? So amongst all the possible subarrays, I want to find the largest sum subarray. Okay, that's the task here. I hope you understood this, right? So just think about it. How many subarrays are possible here? How many subarrays are possible? So my subarray could start from any index I and could end with any index j. Look at this, right? It could, see, as long as, the most important thing here is my I and j could be any two numbers here, right? My I, as long as j is of course greater than equal to I. That's all, right? So my j, as long as it is greater than equal to I can pick any pair of I and j. Again, I is greater than equal to 0. J is strictly less than n. Okay, or we can say less than equal to n minus 1. So as long as I can pick pairs of numbers, look at this, as long as I can pick pairs of numbers I and j, for every I and j which satisfies this condition, for every I and j that satisfies this condition, I'll get a subarray. Now, again, we'll see some brute force solutions and all later. But in this given problem, in this given example, the largest sum subarray starts at this element. You can verify this. Okay, it starts at this element and it ends at 5. Okay, so this is the largest sum subarray. Now, if you notice, 4 plus 1 is 3. 3 minus 2 is 1. 1 plus 1 is 2. 2 plus 5 is 7. Now, if you notice, very important aspect here, a very important and a very neat concept here is the largest sum subarray could consist of negative numbers also. Okay, so many people think that the largest sum subarray cannot consist of negative numbers. Here, the reason we have a negative number as part of our largest sum subarray is because if I took only this subarray, imagine if I just selected this subarray, the sum equals to 5. If I just selected only this subarray, the sum equals to 6. But if I let this array grow to the right side, even though there is a negative number here, because there are more positive numbers on this right side, right? Eventually, I'm getting a larger number here. And it is possible that there could be multiple largest sum subarrays with the same sum. Okay, this value is unique. Okay, because we are saying it's the largest sum to start with, right? But a very important thing notice in this example here is you could have negative numbers as part of your largest sum subarray. That's a very important realization. Okay, I hope you understood the problem itself. With this basic introduction, let's dive into tackling this problem. Again, I've just copy pasted the same array here. What will be my brute force solution? Let's not worry about designing a optimal solution. It's always good to think about it from a brute force perspective first. Okay, look at this. My I could be here, my j could be here. So what if I have a loop like this? Okay, because my I and j can satisfy these conditions, right? Look at this. My I and j simply need to satisfy these conditions, which means, look at this, 0 less than equal to I, which is less than equal to j, which is less than equal to n minus 1. That's all. So I can actually write this trivially as two loops, right? For I equals to 0 to n minus 1, right? For j equals to, look at this, for j can be greater than equal to I. So j equals to I to n minus 1, right? So now what do I get? I'll simply compute the sum of elements from a, I up to j. Okay, let's assume this is the array from ith index to the jth index. I'll just compute this sum and I'll keep some global variable here. I'll keep some global variable called max sum, which I'll initialize it to a very small value, right? And if max sum, and simply what will I do here? I'll just say if max sum is, okay, let's call this s. If max sum is less than equal to s, then max sum equals to s. Right? That's it. So if you think about it, this is like a twin loop. I have a loop for I have a loop for j. Okay. This I can go from 0 to n minus 1. This j can go from 0 to n minus 1. Sorry, this j can go from I to n minus 1, not from 0 to n minus 1. But we have seen such loops, right? And this is the simplest one. If you just write this twin loop, this nested loop or nested twin loop, you get all the possible subarrays in this array, right? And if you think about it, we have seen this from the very beginning of data structures algorithms. Whenever we have a loop like this, the time complexity is obviously order of n square, right? So this is my order of n square time complexity. My space complexity is order of 1, right? This is simple. So the brute force algorithm here is giving us order of n square time space complexity of order of 1. Cool. Now the big question here is, can I improve upon it? Okay, that's the important question. Can I improve on the brute force? Look at this. What is my brute force giving me? My brute force is giving me order of n square time and order of 1 space, right? Can I somehow try something else? Okay. What could be considered better than this? Can I get order of n time and maybe if I can even get order of n space or better, okay? Or if I can, or better, for example, if I can get order of n time and order of 1 space, that's phenomenally good, right? So the idea here is, can I somehow improve upon the brute force? The brute force is trivial, right? The brute force is a trivial algorithm. Like anybody who knows basic programming can come up with this solution, right? It's a simple twin loop solution. We have seen tons of algorithms like this, right? Now comes the fun part. How can we improve upon this? And this is where the fun starts, okay? Now there are multiple ways to think about it, to be honest with you, okay? So one strategy, my favorite strategy always, when we have such problems, is to think of a recursive solution. And you might wonder, why am I jumping to recursion here directly? Or how am I jumping to recursion? My thought process is like this, okay? Recursion is the basis of all of dynamic programming, right? If you think about it, recursion is the basis of all of dynamic programming and also greedy algorithms to some extent, right? Because as we have studied in the course videos, dynamic programming effectively is overlapping subproblems, right? Is basically overlapping subproblems and optimal substructure, right? Along with plus optimal substructure. What is optimal substructure? Optimal substructure basically means recursion. Similarly, greedy algorithms are nothing but your greedy strategy, or they satisfy the greedy property, right? They satisfy the greedy property, as we have seen some of the algorithms, plus optimal substructure. And what is optimal substructure? Optimal substructure is nothing but recursion. Okay, that's why in many programming interviews and in many instances, recursion is given so much of importance, because recursion is the foundational concept for more advanced strategies like dynamic programming, greedy algorithms, even divide and conquer, right? If you think of even divide and conquer algorithms effectively are nothing but recursive solutions, right? So if given a real world problem, if you can write it as a recursive problem, right? And once you write it as a recursive problem, you can either leverage all the machinery that we learned about divide and conquer strategies. We can also probably map it to dynamic programming if it has overlapping subproblems. Or we might be able to map it to a greedy algorithm if it satisfies the greedy property or greedy strategy, right? So that's why my favorite strategy, again, I'm not saying this is something that will always work, but this is something that we should always keep at the back of our mind, because some of the most powerful algorithms that we've studied in data structures and algorithms are based on recursion, because recursion itself is the foundation for divide and conquer, dynamic programming, and greedy, right? So whenever your brute force, for example, your brute force gave us order of n square and order of 1 space. Okay. And this seems like, if you look at this, the largest sum contiguous subarray problem. I mean, we have seen problems like LCS, for example, right? Which we comfortably broke it into dynamic programming through recursion, right? So the idea here is, if I can somehow, again, I don't know whether I can write it recursively also or not, but recursion is something that you should always keep in your toolbox, right? If you can write the problem as a recursive problem, then you can either apply dynamic programming strategy or a greedy algorithm strategy or a simple divide and conquer, simple recursion. Because the moment I map a problem to recursion, all these things open up based on whether I have overlapping subproblem or greedy or not, right? So it's always good to always keep in mind that given a problem, oh, can I actually write it as a recursive problem? That's something which is extremely useful to think of. So now let me design this. Given this problem, again, we don't know how to write the recursive formulation itself. So let's do some experiments. We might fail in some of them. In the real world, when you are actually in an interview setup, it's not always guaranteed that you'll write the most appropriate recursion formulation in the very first go. Okay, not always necessary. Even today, when I solve problems like this, the very first time I try to pose this problem as recursion, I don't always get the best solution in the first go. But I know how to find the mistakes in my solution and move towards the right solution. That is important. Okay. So not knowing, see, it's unless you're an expert, unless you have solved hundreds of recursive problems, you'll not be able to map it directly. But if you think about it broadly, in recursion, what do we do? Okay, let's see. In recursion, the examples that we've seen in recursion, right? In recursion, given a problem of size n, we map into problems of size n by 2 or n by 3, etc. Okay, we break into much smaller pieces. This is one strategy. The second strategy that we have seen is, given a problem of size n, I'll try to break it down into problems of size n minus 1, n minus 2, etc. Okay. Again, this problem can be solved by both these approaches. Okay. I'll pick one of them. Okay. I'll try to pick the second approach, wherein I'll try to map a problem of size n into problems of size n minus 1 or n minus 2. So I'm not doing it as a ratio like n by 2. I'm not doing n by 2, n by 3 or n by k. I'm doing n minus 1, n minus 2. Again, you can solve this problem even using this strategy. Okay, there are multiple ways to write recursion, and there are some wrong ways and some right ways also. So let's start with something simple. Imagine I define. Okay, I'm just trying to define something here. Again, I don't know whether this will work or not. Please, I don't know whether this strategy will work or not. I'll try a few strategies. Imagine if I define L 0i. Okay, I'm trying to define this. I write L0i as the largest sum subarray. I write this as largest sum subarray. Okay, largest sum subarray using elements. Okay, the actual sum itself, I'll represent it as L0i. Largest sum subarray using elements from A0 to AI. Okay, this is what. So let me define this. Let me define this expression here. Now, if this is the expression that if I define L0i as the largest sum subarray using this, I don't know whether this will work or not, to be honest with you. Okay. Now, what do I want to compute? I want to compute. If this is how I define my L, if this is how I define my L0i, what do I want to compute? I want to compute L0 n minus 1. Okay, because what is L? 0n minus 1. It is the largest sum subarray using a0 to an minus 1. And that's what I want. Right? Now let's see if I can even solve the problem. Please remember that writing the recursive formulation is one of the most creative and the most important. This is one of the most creative aspects and the most important aspect. Okay, there is no formula to do it. If there was a formula, all cracking any programming interview would become a joke. Okay, this is something where you have to be very creative. You will make mistakes. Okay, so let me give you a hint. This doesn't work. Okay, I've intentionally chosen a strategy that doesn't work because I want you to experience strategies that don't work and understand why it is not working and go in the right path of solving the problem appropriately. Okay, so it's not necessary that you will get the best approach in the very first go. So let me define this way. Let's start somewhere. Okay, seems like a reasonable idea at the outset. I don't know how to solve the problem yet. Okay, so now let's go step by step. I'll compute L00. Okay, what do I want? I want to compute L0n minus 1. This is what I want to compute. So let me represent this. Let me try to break this down into smaller problems. Right? That's what recursion is, right? Into smaller problems. Okay. So let me try some strategies. Let me understand how to actually break this down using some examples. So let's say L00. What is L00? L00 is basically just this subarray. What is the maximum sum subarray? If I just have this, it is only minus 2. The maximum sum is only minus 2. Now, if I have this solution, so I have L01. Now using I have L00. Using L00, can I find the solution for L01? Look at this. I have L00. I'm trying to use L00 to compute L01. If I can somehow solve it recursively, I can finally arrive at L0n minus 1. That's my strategy. I don't know whether this will work or not, but let's give it a try. Okay. Now, okay, this is my 0, this is my 01. Now this is my subarray, right? In this subarray, I want to compute L01, okay, which is the largest sum value itself in this subarray. Now, if you think logically, what should that be? Again, when I'm writing L01, I want to write it in terms of L00. Okay, so it can be max of these three things. If you think logically, okay, it could be the max of L00, which means only this term is my maximum sum subarray, or it could be just this one. This is just my maximum sum subarray, or it could be these two together. Right? There are three possibilities, right? If I have two values, there are three possibilities. So what is the previous one? L00 or A1. Look at this. A1 is just this, or L00 plus A1. Very good. So now what is L? So let's write the values here, right? What is L00? Minus 2. What is A1? A1 is minus 3. What is this? This is minus 2 plus minus 3. Minus 5. Which is the max of all of them? The max of all of them is minus 2. Right? So L01 is minus 2. Very good. Okay. Now let's continue. So I got L01, L00, I got L01 also. Now I want L02, which means I have this subarray now. Okay, I have this subarray 0, 1 and 2. Now again, I want to represent L02 in terms of L00 and L01. Okay, preferably in terms of L01. Okay, then my recursion becomes much more simple. Again, whatever strategy we employed here, I'm employing the same strategy. Imagine I have the max subarray of, imagine I have the max sum subarray of L01. This itself could be my solution, or this itself could be my solution, or my solution could be the sum of these two. Same strategy that I'm trying to apply. Now, does this work? On the surface, it seems to work. But let's see. What is L01? L01 is minus 2. What is A2? A2 is 4. What is this? This is minus 2 plus 4. But is this valid if you think about it? Is this valid? See, I want a contiguous subarray. Look at this. Look at the problem definition itself. If you look at the problem definition itself, I want the contiguous subarray to start with. But now if I go down this path, again, I don't know whether the solution will work. I'm just experimenting. If I go down this path, right, what is my sum of minus 2 and 4? And that's not allowed because minus 2 and 4 is not a contiguous subarray, which means this whole approach is failing. This whole approach fails here. The moment, see, it worked when I have only one element, it worked when I had two elements, but the moment I have three elements, everything is failing. I hope you understood this, right? And why is this failing? Understanding why this is failing will give us new ways to think. Why is this failing? Because in L01, look at this, very, very important aspect here. In L01, right, the maximum sum subarray is only -2. Okay, the last element here is not part of L01. That's why when I add this, it is no more valid. Look at this. My L01 is -2, right? It's only -2, which means only this element is there in L01. This element is not present in L01. So when I do L01 plus A2, everything is breaking down because my contiguity is being broken because this element is not part of the solution of the smaller subproblem, right? See, when I'm trying to solve L02, my smaller subproblem is L01. And L01 does not have the first element. That's why everything is breaking down. So what is the lesson learned? Okay, we'll come to the lesson learned. First thing, it's failing. Why is it failing? Because when I'm computing L0i, okay, as a way to compute L0i plus 1, see, as a way to compute L0i plus 1, I'm computing L0i. But in this solution, if ith element is absent, right? If ith element is absent in this solution, then this solution using this sort of max is not valid, right? Which means the whole way we formulated a recursion itself is incorrect. It's not working out. But what is the major lesson learned here? And the lesson is the important part. It's perfectly okay to make mistakes like this, but the lesson learned is the important part. The lesson learned here is the absence or presence of an element is more important, okay, than anything else. And that's something that we have not accounted for in this formulation, in this recursive formulation. Again, coming up with the appropriate formulation of recursion is the most creative and most important aspect. Intentionally, I have chosen a way which does not work to show you how things fail and how to learn from failures. Okay, now what is the lesson learned? The lesson learned is presence or absence of an element is the key idea. So if I want to solve a problem, if I want to compute the largest sum from 0 to I, okay, what is important here is to know whether I minus 1 is present or not. If I minus 1 is present in that largest sum subarray, then I can simply concatenate I because that will become contiguous. That's a key idea here. So let's reformulate based on this learning. Let's rewrite the whole definition itself, right? So now I'll define, so I'll just skip 0 now. I don't need it, okay? So now I'll write Li as the largest sum. Again, look at this. I'm redefining this whole thing. Here L0i is the largest sum subarray using 0 to I. Okay, here I'm redefining the whole thing because we learned that presence or absence is the important aspect here. So I write Li as the largest sum subarray, right? The largest sum subarray which contains, okay, which contains the ith element. That's important, right? Which contains the ith element, because if I know if it contains the ith element, I can compute Li plus 1, right? So largest sum subarray which contains the ith element using all elements in A 0 to I. Look at this. The second part is the same as the previous one. The largest sum subarray using elements from A0 to AI. But here we want the presence or absence of ith element to be the important aspect. That's very, very important. Now let's try to write some recursive formulation. Let's try. So L of 0 is equal to A0. Obviously, okay, because think about it, right? If I have A0 here, if I have only one subarray, okay, if my subarray only consists of one element, obviously, what is the largest sum subarray? It is just A0. So this part is clear. Now, if I have a problem, if I have a solution, look at this. If I have a solution for a subarray, if I have, let's say L, so let's write it this way. If I have Li minus 1, if I have a solution for Li minus 1, okay, which means this is the largest sum subarray which contains the I minus 1th element. Then can I write Li as two pieces, two possibilities are there. It is a max of, okay, two possibilities are there. So let's assume I minus 1. Let's assume I minus, so let's compute Li minus 1. What does this give me? This gives me the maximum sum subarray, or it gives me the largest sum which contains the I minus 1th element using elements from 0 to I minus 1. Which means this is now part of the solution, which means now I can add this to it. The contiguity is not broken. So I can add AI to this. Either this is my best solution, or if I minus 1, see, it could so happen that, again, this is the second case. If I minus 1 is not part of the solution, then my largest sum subsequence can be just this, or something that starts from here. If this element is not present, then I cannot take anything, I cannot use anything that is there in this piece. If this element is absent, right? Because it will create this gap, right? Contiguity is broken then. So the max of this and AI, right? What is the first case? First case says that the I minus 1th element is present in my largest sum subarray. To that I am adding AI. So this ensures that I don't break the contiguousness. That's one possibility. Second possibility here is that I minus 1 is not there, which means I can't use anything in this region. I have to start afresh from this region, which means my maximum sum subarray will be AI. Whichever is maximum of both of them will be my Li. So now we have found a way to compute Li recursively, right? We have found this. So this formulation seems to make a lot of logical sense. But we haven't yet solved the whole problem, right? We haven't yet solved the whole problem, because what Li is giving me is the largest sum subarray which contains the ith element, right? Using all these elements. But my final, what do I finally want? I want the largest sum subarray. Look at this. I want the largest sum subarray, right? Using elements from A0 to n minus 1. Whether AI is present or not is immaterial to me, right? So what you actually want, again, this is not the solution. Many people confuse here and think Ln-1 is the solution. No, Ln-1 is only giving us the largest sum subarray which contains the n-1th element. The actual solution to the largest sum subarray in this array may not contain the n-1th element. So what we actually want, this is important, our actual solution or max value, if you want to call it, the max value that we are looking for is the maximum amongst L0, because what is L0? L1, L2, I'll come to justifying this, okay, so on and so forth, Ln-1. Okay, now look at this. So what is this telling me? L0 is telling me the largest sum using largest sum which contains A0th element. So the sum that contains the A0th element, right? This is giving me the largest sum which contains the A first element. This is giving me the largest sum which contains the second element. This gives me the largest sum which contains the n-1th element. The actual solution that I'm looking for, which is the largest sum subarray, I don't care whether one of these elements is present or not. I don't care about it, right? Which means the maximum amongst all these LIs, is what I finally want, right? This is a very, very important aspect. This is where many people get confused. Again, the reason I picked up this problem is because this is slightly tricky. This is not trivial. Many people who are beginners may not be able to absorb that this is the key thing that we want to compute, right? I've seen many people make the mistake that they would say, okay, I've gotten this recursive relation. What I want to compute is Ln-1. No, that's not what you want to compute. What you want to compute is the maximum amongst L0, L1, L2, so on, Ln-1. Okay, so now how do we compute this, and what is the time and space complexity? We have done so much of thought process, so much of hit and trial, so much of experimentation to arrive at it. Is it any better than brute force? Let's see. Suppose if I want to solve a problem for ln or li, for any ln if I want to solve, this will recursively call ln minus 1, right? This will recursively call ln minus 2. This will recursively call and so on and so forth. For example, imagine if I'm solving for ln minus 1, right? When I'm solving for this, to solve this problem, I need the solution for ln minus 2 also, right? Look at this. I need the max of all of them. Look at this. I need the max of all of them. First, I can compute ln minus 1. Then I can compute ln minus 2. So for example, I can easily write a function to do this, right? I can easily write a function because I have the base case. I have the base case and I have the recursive case. It's literally 4 lines of code to compute li, right? Now here is the tricky part. Let's assume I am computing ln minus 1. While computing ln minus 1, I have to compute ln minus 2. While computing ln minus 2, I have to compute ln minus 3 and so on and so forth up to L0. Again, next time when I compute ln minus 2 here, because I want a max of all these values, right? First I'll compute ln minus 1, then I'll compute ln minus 2, so on and so forth. Next time when I compute, so this is my first step, let's say. My second step when I'm computing ln minus 2, again I need ln minus 3. To compute ln minus 3, I need ln minus 4 and so on and so forth. But if you notice, ln minus 3 has already been computed while computing ln minus 1. If I can store this value somewhere, I can reuse this value here. So one thing that you might notice here is something called as overlapping subproblems, right? Very simple to observe. There is overlapping subproblems, right? There is overlapping subproblems. To solve ln minus 1, I need ln minus 3, ln minus 4, ln minus 5, all of that. But to also compute ln minus 2, I need ln minus 3, which means instead of recomputing the same thing, if I can store it somewhere, remember, if I can store it somewhere, I'm done, right? Very simple example. So let's see. Okay, so that's the first key takeaway. The second key takeaway is to compute ln or ln minus 1, whatever, okay? ln or ln minus 1, what is the time complexity? Okay, if given this recursive equation, what is the time complexity? A problem ln is broken down into ln minus 1 plus some constant time. Why is it a constant time? Because once I compute this, adding this value and computing this max is all linear time. Sorry, is all constant time. Is all constant time, right? So what am I doing here? So ln, so you can write Tn, the time taken to solve a problem of size n, is time taken to solve a problem of size n minus 1 plus order of 1. We have seen how to solve recurrence relations like this, right? So to solve ln, to solve a problem of size n, you're solving a problem of size n minus 1 plus some constant. To solve this, again, recursion tree method that we've discussed in the course videos, right? So you again require constant, so on and so forth, up to 0, you again require constant. What is the total time? N into c. The total time is order of n, right? So to compute ln, look at this, to compute ln, I require order of n time, right? But what do I finally want to compute? I want to compute the max of ln minus 1, ln minus 2, so on and so forth. So what can I do here? Because when I'm solving ln, I'm already computing ln minus 1. So imagine if I store this in a table, right? Imagine if I store this in an array, let's say. This is L0, this is L1, this is L2, so on and so forth, ln minus 1. Okay, so this table is not my input array. This is an array of L's. Okay, here I store L0. Okay, because look at this, when I'm solving for ln, I go and solve ln minus 1, which solves ln minus 2, so on and so forth recursively. The moment I compute L0, I'll store this here. The moment I compute L1, I store it here. The moment I compute L2, I store it here. Right? I keep storing this. So now what is the total time complexity to compute all of these values? If I just compute ln minus 1, during the process of computing ln minus 1, I'll compute all these values through recursion. And if I just store them in a table, I'm done. And what is the time complexity to compute ln minus 1? Let's go step by step here, right? What is the time complexity to store ln minus 1? Right? It is nothing but order of n. Right? And in this order of n itself, I'm creating an array called L. Right? I'm creating an array called L. Okay? I'm creating an array called L. And in this array, I'm storing all the L0, L1, L2 up to Ln minus 1. Finally, I'll just compute max of all of them. How much time will it take for me to compute max of all of them? Again, takes order of n time, right? So which means what is the total time complexity to solve this whole problem, to find the maximum value? The total time complexity ends up being order of n time. What is the space now? There are two types of space here. One space for the L array. Okay. So order of n space for the L array. Okay. Where we are storing this. Plus, if you notice, we are also doing this recursion, which means there is stack space. There is also this recursion, right? Which means on the stack itself, I have order of n space. So in total, I'm getting order of n time, and in total, because order of n plus order of n is equal to order of n, right? In total, I'm getting order of n space and order of n time to solve this problem using recursion. Okay. So this is much better than, look at this. This is much, see what did we, our brute force gave us order of n square time and order of 1 space. What this gave me is order of n time and order of n space. And what are we solving here? We are solving using dynamic programming. And why is it dynamic programming? Again, very simple concept here. Very simple concept here. Because I have recursion plus overlapping subproblems. Okay. Look at this. What I'm storing here, what I'm storing here is my memoization, right? Because all these, the solutions to overlapping subproblems, I'm storing in the L array, right? That's what is my memoization. I'm storing solutions to smaller subproblems in this array so that I don't have to recompute them over and over and over again, right? Very simple. This is a standard DP. This is a standard example of DP. But here comes a question. Can I do better than this? Okay, can I do better than this? Very important question. Right now I have order of n time and order of n space. Order of n space. And if you notice, my space is being taken up both by recursion. Again, this is my stack space, right? This is my recursion stack. And I also have the L array. And if you notice, the recursion that we have designed here is called the top-down recursion, right? It's called the top-down recursion. Why is it called the top-down recursion? Because we are starting with a problem of size n minus 1, going to a problem of size n minus 2, and so on and so forth up to a problem of size 0. Can I now take this recursive solution, okay, which is a top-down recursion? Okay, what I have is a top-down recursion. Can I now convert this into an iterative algorithm smartly? And if I convert this into an iterative algorithm, can I somehow decrease this? Okay, that's the key aspect here. This is a very interesting problem of converting a DP problem, which has order of n time and order of n space, which is a top-down recursion. Can I do something like a bottom-up recursion here, wherein I'll try to reduce this using iteration? Because one of the reasons this order of n exists is because of stack. Another reason is because of the L array. Can I completely avoid both of them using iteration? Very interesting step, right? So let's look at this. So here is an iterative algorithm that solves the same problem. The concept here is very similar. Okay, this is an iterative algorithm. This is often this is also referred to as the Kadane's algorithm. Okay, very popular algorithm. This is a standard, like this is a phenomenal algorithm wherein you take something which is a DP problem, which takes order of n time and order of n space in the top-down recursion. You convert this into iteration and finally obtain the time complexity doesn't change, but the space complexity changes to order of 1 space. Okay, so let me walk you through how this is happening. Again, what we have seen is top down because we are starting from n minus 1 to 0. Here we'll do a bottom up, which means we'll start from 0 and go to n. Okay, so let's go through each of these steps here. Here is my function a, number of elements is n. I'll initialize max sum. This is the final result that we want. Okay, this is the maximum sum amongst all the subarrays. I'll initialize it to a0. Max current basically means this is the maximum sum subarray which includes the current element. Right? So initially my element is 0, so I'll say a0. So this includes a 0th element, and this is the maximum sum subarray which includes the current element. Now if you look at this loop, this is a for loop from I equals to 1 because 0 is already accounted for here at initialization. This is my initialization. with index 0. So this is from 1 to n minus 1. Look at this. This is exactly the recursive formulation that we have seen. This formulation, if you think about it, this is exactly the same as this, right? This is exactly the same as max of this plus this comma this. This line is exactly the same. It says maximum sum subarray, which includes the current element, is just the current element or the maximum sum subarray, which includes the previous element that I have plus this element. It's a max of both of them. Okay, this is how we defined it recursively, right? The same recursive formulation, we are using it here. And now what we say here is, if max sum, okay, the max sum that we have is less than max current, okay, which means the final solution or the global maximum that we want, if it is less than the maximum sum which includes the current element, then max sum equals to max current. That's it. Simple loop. Return max sum. Literally 6 lines of code. Literally in 6 lines of code, you can solve this whole problem. Okay. But what is important here is not the solution, but how you arrive at the solution. This is called as the Kadane's algorithm. Here, again, this is called bottom up because we are starting from the 0th index and going up to the n-1th index. And if you notice, we are using the recursive formulation here. And if you look at it from a space and time complexity, since we are not using stack, this is gone. The L array is also gone. Remember, the L array is also gone because the L array's values at any point of time, I'm actually storing it in max current. Right? Look at this. What does max current? At any point, if my I equals to, let's say, at any value I, what do I get here? What do I get here? I get Li here. At this point of execution, after this line has been executed, for any value of I, right? If I equals to 10 here, I get L10 here. I'm computing L10 here and I'm comparing L10 with the best value that I have now, thereby completely avoiding storing the L array itself. Why were we storing the L array earlier? Because of overlapping subproblem. Now, since I'm not solving the problem recursively, I don't have the whole problem of keeping track of the L array itself. Okay, I'm just simply throwing away the L array by comparing with the maximum sum now at any instance of time. So now if you look at this, there are a bunch of there are constant number of variables here. That's why this is order of 1 space and order of n time. Kadane's algorithm is one of the beautiful algorithms which takes a fairly simple looking problem. Okay, the largest sum subarray is a simple looking problem, but the way you arrive at it. So again, let me show you the steps that we arrived at it, right? We started off with brute force, right? We tried a recursive solution, okay, recursive solution 1, which failed, okay? So we learned that presence or absence is important, okay? So lesson learned here is presence or absence is important, okay? The presence or absence is important. From this lesson, we arrived at the recursive solution 2, okay? And we realized that this has overlapping subproblems, and hence this is a dynamic programming. From this, and again, we saw that this was a top-down recursion. So we said, can I do a bottom-up iteration? Instead of a top-down recursion, can I do a bottom-up iteration? And bottom-up iteration is nothing but your Kadane's algorithm. Your bottom-up iteration is nothing but Kadane's algorithm. Look at the series of steps that we have logically followed to arrive at Kadane's algorithm. Again, this thought process and this problem-solving ability, most important of all of this is when you try an approach like this. See here, I've tried an approach. It fails. In the real world, when you solve problems, when you try to write the recursion, especially early in your career, or if you're a beginner in data structures algorithms, you'll fail a lot. You will need to be very creative, and most importantly, you need to think of all the cases and especially understand why things are failing, so that you can write a better or a more appropriate form of recursion, right? And once we have the recursion, right, understanding overlapping subproblem was straightforward because it is clearly visible to us, right? It was very clearly visible. Overlapping subproblems were staring at us. Once I have overlapping subproblems, again, I got the top-down solution. From the top-down solution, we asked, do I actually need to store the L array? Do I need to use the recursion stack? Can I somehow avoid them? And from that came the bottom-up iterative solution, which is nothing but the Kadane algorithm, right? I hope you have got a good appreciation of this technique now.